I'm sharing my screen. Hope the screen is visible.
Yes, ma'am.
Okay. Let's wait for 2 more minutes, then we'll start. Hope you all have revised what we have studied so far. Last class, what we have studied, we have taken a member, we cut the member, then we have analyzed for nominal stress, true stress, nominal strain, true strain, right? Today, basically, we'll discuss the stress strain diagram. Okay, what is actually a stress strain diagram? Maintain your notes. I'll share the notes today. I think I have shared till third lecture. I'll share the rest of the lecture today for both the sections. How many students join? Okay, 33. Perfect. We can start. Okay. So today we'll discuss, and the both class will discuss basically what is stress strain diagram, purpose of this diagram. Then we'll go for material properties associated with stress strain diagrams and Hooke's law. Please remind me if my voice and screen is not visible at any moment. Okay. So just before that, let's do a review what we have studied so far. Uh, we have taken a member, right? We looked at exocentric loading where we applied an external force to a member. It stretched out and became long in length, which is represented by delta. We did a transverse cut to this member and we found that normal force is equals to P. Okay, and we talk about the concept of stress, which is force per unit area perpendicular to the cut surface, and then we discussed the strain, which was elongation per unit length. Okay, and these were the two types of stress: nominal stress and true stress. Nominal was force per actual area, and true stress was force per the area which we got after the body gets deformed. And in strain, change in length by original length, and in true strain, this was the true length and it was the length after deformation. So these were the basic review. Okay, let's move to the next slide. So stress strain diagram. To examine material properties, we can perform tension test. Google about tension test. You will get lot of videos in the YouTube. You can search it and you can see the video of tension test. Okay. So to examine material properties, we can perform tension test. In graphing the results, we'll plot stress strain instead of force and change in length. In time, we will always plot stress and strain value, not force or change in length. Okay. To know the material behavior, we discuss those behavior in terms of graph, which is stress strain graph, and we plot here stress and strain instead of force and change in length. This allows for the removal. Why we do this? Allows for the removal of geometry from the problem and allows the results to be used for different geometrical shapes of the same material. Okay, suppose I'm taking a steel of steel is a material, but suppose we have different geometry, right? So for different geometry, there will be some different cross sectional area, different change in length. So we don't take this and this. We generalize take a stress strain curve for a material steel. Suppose you have steel. Suppose you have T section of steel, okay, and one I section of steel. This is T section and this is I section. Okay, so you if we take force and change in length, then we cannot assume a single curve for these two. And if we take stress and strain, we can generalize a single graph for just steel. So that's why we are taking stress and strain instead of force and change in length. Hope this point is clear. Okay, we'll discuss this curve very brief, in explanatory way, but there is just a brief. This curve basically has two main parts, a linear part and a non-linear part. Okay, in the linear part, your stress and is directly proportional to strain. See, suppose I'm taking a point here. So what is the stress at this point? That will be a strain. What is the stress? Strain. So here stress is directly proportional to your strain in linear part of the curve, and here there is a non-linear part of the curve. At this point, till this point, your member, your structure or your material will come back to its original position when it gets deformed. Okay, but from this point to this point it starts yielding it. Suppose I'm taking a point here, and when the material comes to this point, your structure or material will not go back to its original form. Okay, and after getting stress at some point it will get fracture. Suppose I'm taking an example of spring. Suppose I have a spring, very tight spring, I'm stretching it. Okay, I'm stretching it. Some after You can imagine you are stretching a spring, it will deform to its original shape till some point. After some point, when you stretch, it will get elongated, right? It will get elongated. So when it starts elongated, that this point starts. You can call yield. Yielding has been started because it won't come to its original form. Whenever you applied force, it will get elongated and elongated, and at some point it will get fracture. So basically, this is your non-linear part. This is your linear part. Okay. Any confusion with this part? Hello? Any confusion with this part? No one is saying so. I hope no issues. Right? Shall I move to the next part? Are you guys there? Hello?
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Someone is waiting in the lobby. Let me admit him. Let's move to the. This is the brief diagram of the stress strain diagram. Okay. So suppose I'm taking a ductile material, or I have plotted a graph of rubber. Okay. The same way, this will be the elements of a graph. Your graph will be similar, but the shape can be different. You can draw a stress strain diagram for aluminium. You can draw for steel. You will find it in the over the net that different stress and strain diagram will be there for steel, aluminium, alloy. Every different material will have stress strain diagram, but these elements will be same. This element, this element, this element, and this element. It will have a linear region, and this part is basically nothing but your non-linear region. Okay, so let's discuss this graph. So let's start. In the x-axis you will have your strain, and in y-axis you will have your stress. Okay, so we'll start with zero stress and strain. Okay, I'm starting with zero stress and strain. This is my 0 point. I'm starting, suppose I'm taking a spring, very tight spring. Okay, I'm taking a very tight spring. So this is your starting point. I'm stretching this spring. I'm stretching this spring until some point. Okay, this is your first point of the curve. Till this point, your spring will come back to its original position whenever you stretch. Okay, so this point till this point, see the shape of this curve is straight line. Okay, so this point on the curve is in a strain part, it is called linear region. Why linear region? Up to this point your spring will come back to its original position whenever you give a stress. See, at this point, whatever be the stress, that will be a strain. Suppose you are taking a point, whatever you taking the stress, it will give a point of strain, right? So this is your linear region part. This is a linear region part, and slope of this part is, this slope is nothing but your E value. And hope you are familiar with E. What is E? It is Young's modulus. Okay, and a point on this curve stress part, it is called proportional limit. Why it is proportional limit? Means whatever you apply a stress, you will get a strain. Okay, whatever you apply a stress, you will get a strain in this part. So this is your nothing but linear region, and this is called proportional limit. Why proportional limit? Stress is directly proportional to strain. Whatever you apply a stress, you will get a strain, and the slope of this curve is, this part is E, which is Young's modulus. We'll discuss this more about in next classes. Fine. Now see, your shape of the curve starts deforming this part. Okay, now your structure is not proportional here. Whatever you give a stress, you won't get a strain, you will get more strain. Okay, suppose you are giving a small of stress, you will get a little bit of strain. But till this point, our structure or our material or our member, whatever you are taking, it can come back to its original position till this point. So this region is called as elastic region. Okay, don't get confused. In elastic region, you have two region. One is linear region. This is a, till here you have linear part. This, from this part to this part, this is non-linear part. So we have a small non-linear part in the elastic region. I have understood. We have small non-linear part in the elastic region. Till this, and this point in the stress is called as yield stress. Okay, we'll discuss this. First we understand, so elastic region comprises of a linear region and a small part of non-linear region. In the linear region, if you apply a stress, you will get a strain. But in small part of non-linear region, that won't be same. But your structure can get its original form, or it, if we give a stress, it will be strained, but if we remove the stress, it will come back to its original position. Okay, so this point is called yield stress. Means after this point, your structure or member or whatever material will be, it will be start yielding. It will be show your, from next stress, it will show, it will start showing you its deformation. So whatever you give stress on it, it will get slightly deformed. Okay, this is the starting point of a body or structure or material to start deforming. Okay, and this region is called elastic region. See, I'm just taking an example of simple, but any member can be. Every member will deform at certain point. But see, this is the general conception of every material in the world. Okay, it, every material have its elastic region. At some point, it will get back to its original position. Okay, but after some point, it will start yielding. It will show you deformations. So that is the concept. Hope this part is clear to you all. Any confusion? Please clear. Further discussing this part, just be clear. Any confusion, any question, you can type in the chat box. Some are not able to get in to participate in the lobby. Okay, admitted. Admitted. I have admitted them. Okay. So any questions you can type in the chat box till this part. Am I audible? Am I audible? I'm admitting.
Yes, ma'am.
So any question, please type in the chat box. Any general question, whatever it is, stupid question, whatever it is, nothing, no question is stupid question. Okay, no question is stupid. Whatever you are getting, see, this is very practical. You should find interesting in things. Okay, so just ask me any question, any doubt. Nothing. 45 students, no doubt. Ma'am, where is the upper yield point and lower yield point? Good question. Upper yield point and lower yield point. This will be your upper yield point. This will be your lower yield point. Okay, I have not, in this part, this proportional limit and yield stress, there will be an upper yield and lower yield point. I have not described that. I'll describe it later in the brief discussion. I'm just explaining the main parts. Okay, Atul, hope it's clear. We'll discuss this part, upper ill point and lower pinpoint. So in this area there will be 2 points, upper ill and lower ill point. Okay, we'll discuss. But right now we are discussing the main parts. Hope Atul is clear. At this region there will be an upper ill and lower ill. Any more questions? See, this is why we are taking a live class, right? Because this should be an interaction class, so that you can ask. You should feel that you are taking the class in you're taking the class in the classroom itself. If you don't respond, then how will I understand? No, you are getting my points or not. I'll simply do lecture and we'll go. Ma'am, what is that E? Okay, this E is your slope of this curve. Your let me note. Your E is your slope of this curve, and it is represented as Young's modulus. You will understand this is Young's modulus. Okay. Uh, let me discuss the Hooke's law itself here. This is the slope of this curve, and this E is defined as Young's modulus. We'll discuss Hooke's law in the next class. For the time being, you know that this E is a slope of this curve. Every curve has slope, right? If you draw a slope of this, there will be a slope. But slope of straight curve, which is in which stress is directly proportional to strain, and that slope is called as E, which is Young's modulus. Any more questions? Any more questions? No. Okay. I'm moving forward then. Okay. Let me note once again. Okay. So till hope this part is clear. Now after this point, if we give a stress, you will get a strain. Okay. Whatever a small amount of stress you applied, it will get deformed. Okay, it will get deformed, and I have represented by this part, means it will be a very long section. Okay, suppose I'm taking a small spring. If you stretch it, it will be slightly get deformed, which will come in under this section, and after that it will get deformed and deformed. Okay, whatever you give stress, it will get elongated. So this part is your perfectly plastic part. Now your structure from elastic region, it comes to a plastic part. Okay, whatever you give stress, a small stress, it will get deformed, it will get elongated. Okay, suppose this is my small spring. I'm applying at this stage, at this plastic region, whatever you give stress, it will get elongated. Suppose this much, again I give stress, again it will get elongated. So it will elongate it up to a certain limit. Okay, suppose up to this point. So this region is your perfectly plastic yielding. Now after this point, it gets the shape of the curve changes. Okay, it will get elongated, it will give you strain, there will be a change in elongation, but there will be a point, highest point, which is called as ultimate stress. This is the ultimate load or ultimate stress a material can take. Okay, this is the ultimate stress a structure can take. Then this part is called strain hardening part. Okay, we'll discuss brief more explained ways in next classes. So this is your strain. After plastic, you will have strain hardening region, where you will get the highest stress a material can take. So after this point, your structure will it starts breaking, or it will get fractures. Okay, and this part is called as necking. Okay, now what is true stress? I have given you two type of stress, right? One is nominal stress. What was the formula? N by A naught. A naught was original area, right? And what was the true stress? It was N by the area which we got after deformation. Okay, so now this area is high, or this area, this, which one is more? This is your nominal stress. At this point you will get a stress of nominal stress, and If you go for a true stress, your curve will go in this direction. This is the engineering stress. We are taking a actual area. But if you want to find a true stress, your curve will be in this direction, upper direction. Why? Because this will be more, right? This area was less, so this was more. So your curve will go in the upper direction. So this is your true stress and this is your nominal stress. Someone may ask you, someone may get confused how this true stress comes up in upper direction and how this uh, nominal stress comes in lower direction. Just just think conceptually. You see, let me stop anything and show you the previous slide. What was the nominal stress? It was force per unit area, which was original area, and true stress was n by area which we get after deformation. So this area is less, so this will be high value. This area is more, so this was low value. So this true stress is high, so it will go upward direction. It will go upward direction. Okay, and this another nominal stress will come to the downward direction. Clear this part? This part is clear? So please respond. Or you have just joined the class and skipping. Respond. Any confusion? No. Sabina, confusion? No. Yes, ma'am. No, ma'am. What about others? 45 participants are there. 49, sorry. Including me, we total are 49. What about others? I'll take a surprise test someday. So go through. As see, in baby class, I'm just discussing a very little thing. Okay, and little small topics, so that you can get a clear picture of this whole subject. So clear your doubts in the class itself. Okay, everyone is saying no doubts, no doubts. So fine, let's move. So now this comes here. Here comes your Hooke's law. In the next class, we will discuss what are the properties associated, means why we are more interested in stress strain curve. Because from this stress strain curve, we'll get the material properties, different material properties. What are the properties a material has? Okay, we'll get all this from the stress strain curve. Okay, we'll discuss that in the next class. But for before that, let me discuss Hooke's law. So Hooke's law is what? Nothing but your stress is directly proportional to your strain. Okay, stress is directly proportional to your strain. When you remove this directly proportional, this stress is this directly proportional is removed by a constant. Sorry, this was E. Let me remove it. Your stress is represented by sigma, right? Stress is directly proportional to epsilon, which is strain. In this region, this is our curve, this region, stress is directly proportional to strain. What is the meaning of this? What means whatever we give stress, it will give a strain. Okay, whatever if we give a stress of 1, it will give a stress of it will give a strain. So stress is directly proportional to strain, and if we remove this directly proportional, what we get? A constant of proportionality, which is known as Young's modulus. This E is Young's modulus. Clear? See, this E is your Young's modulus. And this E also we'll discuss more on the next class, but let me, as I have shown the slide, let me discuss. So this E your generally represents stiffness. Okay? Your E represents stiffness. Okay? Hope you are clear with this word. What is stiffness? How the structure behaves. Okay, we'll discuss in the next class. So hope this part is clear. Hooke's law is nothing but it says, and it is valid for linear elastic region. Mark this word, linear elastic region. Hooke's law will not apply, it will not apply in this region, it will not apply in this region. Why? Because stress is directly proportional to strain only in this region, and that too in linear elastic. See, in linear elastic region, in elastic region we have two sections, one is linear and this is non-linear, right? And Hooke's law is valid only in this part, which is linear elastic region. Clear? This is very important. Hooke's law valid. A 1 mark question used to comes in your GATE exam or in your competitive exam. Hooke's law valid for. It will give you options. So don't get confused. What is it is valid for your only linear elastic region. Okay. So this is about Hooke's law. So in the next class we'll discuss what are the material properties associated with this curve. Okay. So I would like everyone write your, I'll stop sharing my screen. All of you write your roll numbers in the chat box. 51, 48. Many one of you joined late, right? Write your roll number in the chat box. I'll note it down. And please join with your name and roll number beside that. Suppose Guneshwar Saha equals to 051. It becomes easy for me to track down very easily. So from the next time if you join with your name and along with that write your last roll number. ADT is not required. You can simply write Suraj Jamatia 099 like that. And those who have missed the class or joined late, I'll share. You will get the recording in your ERP. Okay, you'll get the recording in your ERP to go through the recordings also. Okay, perfect. Noted down all the roll numbers. Okay, okay. I'm ending the meeting.